Good afternoon, everyone. Welcome to the last day of online training program GATE 2022-21. And we have two sessions today. The first session is on foundation engineering by Dr. S.K. Prasad sir. So here is the brief introduction about our today's speaker on foundation engineering, Dr. S.K. Prasad sir. He is the professor and head of civil engineering at Vidyavardhaka College of Engineering, VVC, Mysuru. He worked for 32 years at Sri Jayachamrajendra College of Engineering, Mysuru, and 3 years at MS Ramaya College of Engineering, Bengaluru. He obtained his bachelor degree in civil engineering from University of Mysuru, securing first rank and four gold medals in 1982. He obtained his master degree in geotechnical engineering from Indian Institute of Technology, Kanpur in 1985 and doctoral degree in 1996 from University of Tokyo. He was the visiting teacher in 2000 from Indian Society of Technical Education, New Delhi. He was a visiting assistant professor at Asian Institute of Technology, Thailand for in the year 2006 January term. He has published over 175 technical papers in national and international journals and conferences, guided over 70 master's dissertations, and guided three doctoral students. Presently, three more students are working for PhD under his guidance. He has completed several sponsored research projects from JSS MFE, AICTE, and DST. His areas of research interest include earthquake geotechnical engineering and performance-based design. With this brief introduction, I welcome you, sir, for today's session. Over to you, sir.
Thank you. Thank you, Professor Madhushri. Uh, yeah, it's a pleasure that, Madhushri C, Professor Madhushri C is the MC today. And, it's always a pleasure to talk about geotechnical engineering. And this is the last lecture of mine. I believe I have also spoken for the maximum number of times. This is the sixth lecture. I hope I'll be able to complete whatever portions I had thought about from foundation engineering point of view. If you just go back, the way I have covered is the way the popularity is there for different portions of geotechnical engineering in general, foundation engineering in particular. So, like bearing capacity, shallow foundations, deep foundations are most asked, and then the earth pressure. So then all other topics which I'll be covering today will be the ones which may come once or twice. So based on the popularity, historically I have been dealing with this subject. So next 90 minutes we'll try to see the last portions of foundation engineering. Kindly permit me to go to my slide. Yeah, I hope my slides are visible. As I mentioned, I'll be dealing with lecture 6 on foundation engineering. These are the portions which I have in mind to cover: soil stabilization and soil exploration, stress distribution in soil, stability of slopes, stability analysis of slopes. If at all there is some time, I'll try to cover Coulomb's theory of earth pressure. Most of the earlier discussions on earth pressure were with respect to Rankine's theory. There are also problems related with that. So, in case there is time, I'll try to spend a little time on Coulomb's theory of earth pressure. Friends, already you know that geotechnical engineering is one of the popular branches of civil engineering in GATE. Also, from the point of view of overall development in civil engineering, I strongly believe good knowledge of geotechnical engineering can take you forward, because there are lots and lots of opportunities for from geotechnical application side. So one very important topic in geotechnical engineering is subsurface investigation. You know, we build our foundations below the ground. We will not know what is there below the ground before. We'll either have to go deep and see, or use some indirect methods to explore. Only when we know what is happening below, only when we know whether the foundation soil is capable of taking the load coming from the superstructure, we will be in a position to build our structures safely, durably. Here, all these people are geotechnical engineers. They went in for soil exploration, maybe for some huge construction. So when they dug out for finding out how good the soil is as a foundation material, they found this person. They found this, python. Can you see the length of this python? So unfortunately, they found it. Fortunately for them, it was dead. So why I am showing this is, until you dig, until you go and see below, you will not know what is there below, what is near there, below the ground surface. Maybe we are all strong in rocket technology. We can probably predict how good, moon is, how good Mars is. But to see below the ground is a big challenge. And then, many a times we use some indirect methods from that to predict the strength, the durability of soil is a big challenge. So we need to explore how good the soil is at different depths, which is the most suitable depth at which you have to found your foundation, and how the foundation and hence the entire structure is going to perform because of the load transferred from it to the ground below is what is a very important topic of foundation engineering. In the figure here, you see, equipment for taking the boreholes. In this figure, you will see the trial pit actually being excavated, and the engineers are trying to explore the different kinds of soils available from top to bottom. Usually, it will be in the layered form. So, whenever you want to build any structure on the ground, it is the soil below which takes the load. So, whenever boreholes are made, bore samples are taken something like this. Every sample can be different from other. You need to identify the different properties of these samples, and hence, predict how the behavior of ground will be. So, you normally will have a soil report, which is very valuable document for the design and construction of any structure. In a soil report, you may use data like SPT n value or shear wave velocity, or maybe sometimes plate load test also can be conducted. And then you also collect data like water content density, at what depth the groundwater table exists. You try to find out the kind of soil available, and you try to evaluate strength parameters, strength, properties of the soil, settlement properties of soil. Use them to interpret. Basically, you have to identify the soil. I'm sure my colleague Professor Chetan would have talked about soil classification. And then biggest challenge is to decide the depth of foundation. Only when you decide the depth of foundation, you may be able to tell what kind of foundation to provide. These two are complementary to each other. So to determine the type of foundation, you require depth of foundation. To also determine depth of foundation, you need to have a fair idea about the kind of foundation coming in. So then you may also have to say whether the soil can be used as it is or does it require some treatment. You need to evaluate properties like safe bearing capacity of soil, and hence you can suggest this is the most suitable foundation you can go in for. A typical borehole detail would be something like this: soils of different you know types are classified in layered form, and in each of the layer mention will be made about the type of soil available, whether the soil was extracted, as a undisturbed sample or disturbed sample, what is the SPTN value, at what depth the groundwater table is available, and so on. And different locations, borehole details are mentioned, and the location details are also mentioned. Based on this, a geotechnical engineer would be able to identify the foundation treatment for a given structure. I always advocate people that soil investigation is very essential before any project you undertake. Earlier days, it was not considered mandatory. Many a times people just assume some data and manage to build the structures. Today, we don't have every place which has got good type of soil, good soil, and also we are having more complicated structures. Earlier days, if any soil was found to be unsuitable, there was scope to discard that site itself. We can't do that now. So always it is essential that we do site investigation, get the data about the soil, and then do the construction. So just like you go to a doctor and you ask for the treatment. Earlier days, doctor used to identify or approximate certain things and just advocate some medication. Today we have very complicated diseases. Doctors cannot take risk. They would say go for test, go for some pathological test, go for some screening test, and based on the test result, doctor would confirm the kind of problem one has and provide the medication. In the same way here, you need to have the soil report before planning for any construction activity. If it is a very easy site, the structure is also not very important. The amount of money you have to spend for site investigation is less, but you should note that if you don't take up site investigation at all, the total cost of the project will be more, because you can't take risk. You will always think about safer, stronger foundation. You may spend little more for foundation, therefore total cost for the project will increase. But if you provide appropriate amount of expenditure for site investigation, you will see that the total cost will go to minimum. If you unnecessarily spend on site investigation, cost will further increase. This is for a easy site which has good soil. On the other hand, you may have challenging site, more complicated structure coming up. There also, site investigation is essential. Naturally, because it is a challenging site, because you are going in for a challenging structure, the cost for site investigation is going to be more. But you will notice that the total cost is going to come down when you appropriately spend on site investigation. So the message is site investigation is essential, whether it is an easy site or a challenging site. Cost for site investigation will automatically be more in a site where you have a lot of challenges. Otherwise, in an easy site, perhaps you may spend some nominal amount, but definitely note that the total cost of construction is going to reduce if you decide on doing the site investigation in the rightful way. You might always have a question as to at what depth the investigation is essential. Let us say you have a foundation like this at a depth D, say 1 meter. You are going to found your foundation at 1 meter depth below the ground. The soil at this depth is going to take that load. So, is it enough if you take the soil properties at this depth? Is one of the questions normally anybody would have. Please note that whenever you load a structure like this, soil below will be stressed approximately for a depth equal to 2 times B. where B is the width of foundation, the stresses will continue to be acting. At least, when you go to 2 times B, the level of stress due to the new structure could be approximately 4 to 5%. So, it is suggested that it is not enough you take the soil properties at the surface or just at the foundation level. You have to go to a depth of at least 1.5 to 2 times the width of foundation. If the width of foundation is 1 meter, below the foundation depth, you can go for a depth equal to 1.5 to 2 meters and try to find the soil properties. Maybe that the soil properties are uniform from here to here, or it could be different. So the engineer has to plan, decide, and tell what is the most ideal value of SBC to be taken into account. Somehow, I normally feel or normally have seen that many of the soil reports are generally absurd. It means, not much value is given to that. It is only for the sake of, permission. So you need license at the corporation level, you need to produce a soil report. Other than that, no further, serious thinking is there in many cases. But I believe it is important that we give lot of emphasis on good report. Here is one report which you can always say that it is absurd. You just see the bore log detail and have simply, highlighted this portion. The concerned soil expert says that, the kind of soil, he explains it as yellowish brown with gray, silty, clayey sand with traces of gravel. First, see the color. Where is yellow, where is brown, where is gray. It's very difficult to identify anything from this. And naturally, color is only secondary requirement. Physical properties, other physical properties are more important. So, the way he explains yellowish, brown with gray, I think is not very, very essential. Then, what type of soil it is? He says that it is silty, clayey, sandy, gravel. Everything he has put here. But all of us know that according to IS classification, we define the soil by only 2 letters. So it could be gravel, it could be sand. But the way it is explained, it looks absurd. So just gave you one hint about what is a bad soil report. So whenever a soil report is given, it should be such that a person can really visualize what kind of soil exists there. And when he goes there, he should be able to identify, yes, whatever is given in the report matches with whatever is seen in the field. And that is missing in many of the situations. So, one of the important things from soil investigation is that you either will have a borehole or you make an open excavation and then you take out the soil sample and take them to the laboratory and do the test. So, one of the biggest challenges is to collect soil sample in, possibly relatively undisturbed manner, because you need to predict whatever is the properties of the soil in the field. And if it is already disturbed, if its structure is going to be disturbed, it's going to make things very different, because what you want is actually what is there in the field. So to collect undisturbed sample is a big challenge. For that, we use sampling tubes, and there are certain requisite properties of soil sampling tubes which are essential. And to understand that, we have a few of these terminologies which I want all of you to be familiar with. It could be area ratio, it could be inside clearance, it could be outside clearance. So a typical soil sampler would be something like this. At the bottom, it has got a sharp edge, cutting edge. It's also pretty sturdy at the bottom, because that is the one which directly comes in contact with the ground, and that is the one which may be subjected to impact. And then you have a thin walled section on the top. So D1 here indicates the diameter to the inner side at the cutting edge. D2 indicates the diameter to the outer edge. Normally, it is slightly more than that at the top surface. D3 is in the thin wall section, inner edge diameter, and D4 is the diameter to the outer edge. And these are the equations for area ratio. It is, you know, D2 minus D1, D2 squared minus D1 squared by D1 squared. So D2 squared is outer diameter at the cutting edge square minus inner diameter at the cutting edge square divided by inner diameter at the cutting edge square. So likewise, you have inside clearance, you have outside clearance. Inside clearance is D3 minus D1 because likely that in the initial portion the diameter is much less compared to the portion above outside, and outside clearance is D2 minus D4 by D4 into 100. And if at all you want the sampler to be the best sampler, there are certain provisions, certain guidelines for this. It is mentioned that the area ratio should be as small as possible. Under normal circumstance, it should be much less than 25%. But in soft, sensitive soils, and if the work is done for an important work, it should be less than 10%. Inside clearance should be 1 to 3%. Outside clearance should not be more than inside clearance. Walls of the sampler should be smooth and they should be oiled before use so that friction can be reduced, friction can be minimized. Non-return valve permits easy and quick escape of water and air while driving the sampler. So D1, D2, D3 and D4 are already explained. So these are some of the minimum requirements. Only when these requirements are satisfied, you say that the sampler is good. You say that the sampler causes minimum disturbance to the structure of soil. So you might have questions. I would like you people to be familiar with the, equations. Maybe if you by heart also it is good. The degree of disturbance of sample collected by the sampler is expressed in terms of area ratio. If the outer diameter and inner diameter of the sampler are DO and DI respectively, area ratio is given by, we already dealt with, DO squared minus DI squared divided by DI squared into 100. Sometimes the problem may be given that, DO is so much 38 mm, DI is 38 mm, DO is 44 mm, and so on. Then you try to calculate area ratio. So I have taken a typical case when the outer is 44 millimeter, the inner is 38 millimeter, and area ratio happens to be 34.1%, which is much higher than what is acceptable. So if you have something like this is not a good sampler. Maybe if you reduce DO to 42 millimeter or even 40 millimeter, then the area ratio is likely to come to less than 25%, therefore acceptable. Therefore, you should be very clear, and hence, the walls of the sampler should be as thin as possible, as smooth as possible. Then only you may be able to achieve better results. Otherwise, they may cause disturbance to the sample which is collected, and hence, samples may not represent the actual site condition. Here is another question. Which of the following statements is true for degree of disturbance of collected soil sample? First one, A. Thinner the sampler wall, lower the degree of disturbance of this collected sample. So, if the soil sampler's wall is thin, the disturbance is minimum. Thicker the sampler, lower the degree of disturbance. No, you can't accept it. If it is thick, naturally it causes more disturbance. So B is ruled out. Thickness of the sampler and degree of disturbance are unrelated. No, I don't think so. So thickness of sampler and degree of disturbance, they are related. If thickness is more, degree of disturbance automatically is more. Therefore, C is also ruled out. The degree of disturbance of collected soil sample is proportional to inner diameter of the sampling tube. No, it is not proportional to inner diameter. It is, proportional to the inner and outer diameters, or more importantly, it is proportional to the thickness of the sampler. Therefore, D also is ruled out. And hence, by elimination process, we can say that B, C, D are not acceptable, and hence A is the best answer. So for question number 2, the answer is that thinner the sampler wall, lower is the degree of disturbance. Let's move over to plate load test. This is a traditional test. This is one of the popular tests because the test resembles the field condition. Only thing is test is conducted on a foundation or a footing which is smaller in size. How small? Usually we use a plate of size 300 millimeter by 300 millimeter. You can place the plate at the foundation level. Plate is a rigid slab, and then on top of it you keep on loading. The loading is applied either through gravity loading or through reaction loading. And when you apply the load, the plate is going to experience some amount of settlement. Keep on measuring the load and settlement, and then you may be able to identify the desired data like bearing capacity of soil. So in this picture, you see this is the plate. This is the steel plate. Usually, plate is 30 centimeter by 300 millimeters by 300 millimeter in size, 25 millimeter minimum thickness. Therefore, it is quite rigid. And then it is being placed at a depth of foundation level. Okay, so excavation is made up to the foundation level, and then it is placed there. And from the top, through gravity loading, the load is applied, and under the load you try to find out the deformations. So you have the dial gauges being placed to find the deformations. So initial load is applied, you see the deformation. Increase the load, find out the deformation. Keep on doing it is the process you follow, and then plot a graph between applied load and the deformation or settlement. The kind of loading many a times preferred is reaction loading. So in this case, instead of putting the load through sandbags, we are going to use a truss or a reaction beam, and of course and a jack. Just like you use a jack to lift up the wheels of a car when it is punctured. So in the same way you use jack here, and hence keep on loading through reaction loading and see the deformations measured from dial gauges. So this is preferred over the gravity loading case because there you require huge number of cement bags or sandbags. Could be 100, 150, 200. It all depends on how much load it takes. And then you require a solid platform to house all these sandbags. So the two methods by which loading is applied are either gravity loading or reaction loading. And then you plot a graph like this, which is called load settlement curve. So this is how the load is applied, and this is how the settlement is measured. And you have for different types of soils, different types of load settlement curves. Also, that depends upon the density with which it is packed. Well, friends, these are some of the important advantages of plate load test. It provides both the things, two important things. One is load at failure, load at which the shear failure occurs. The other thing is settlement details. So you will be in a position to determine allowable bearing pressure in a better way here because you get the shear failure capacity at the time of shear failure. you also get an idea about the settlement characteristics. So both these factors are to be considered from the point of view of determining the allowable bearing pressure. Two, being a field test, there is no requirement of extracting soil sample. I told you, you need to extract soil sample, bring it to the laboratory and do the test. In this case, not required because it is a test conducted in the field. Therefore, no need to collect sample. You conduct the test directly. Test is similar to the field condition, most important. So in the field, how you load the foundation, exactly in the same way, you actually load the plate, and hence it simulates field condition to the best extent. Unfortunately, and then it's a fast method. You do the test and quickly get the result. So it's a fast method to estimate the SBC or allowable bearing pressure of soil. Some of the disadvantages: test results reflect the behavior of soil below the plate, not for the actual footing. This is what you need to very seriously know. I just tried to show here. Let us say you do the test on a plate of size 30 centimeters, 0.3 meter. The area of influence will be 2 times 0.3, that is about 0.6 meters. So you will see that the area of influence is about approximately 0.6 meters. Any soil below, you don't know what type of soil is it. It may be strong or it may be on the other side. Let us say you have an actual footing which is of size 2 meters. Then its influence is for a depth equal to 2 times 2 meters, which is about 4 meters. So test is conducted only at shallow depth. The area to be considered is only about, let us say, 0.6 meters. Below that, even if the soil is poor, you will not be able to understand. You will not be able to assess. So that's one of the major disadvantages. And it is essentially a short duration test. You do the test for a week or so, but our buildings have to last long, for centuries maybe. So long-term effects are not determined from this test. One of the long-term effects is settlement. Settlement can happen for a month, years, centuries. We don't know, and we will not be able to identify anything about the actual settlement, consolidation settlement. Size effect is very much pronounced in granular soils which have cohesion, which are cohesionless. So correction for size has to be given because size of the plate is very different from the actual size of the foundation. It's a cumbersome procedure to carry equipment, apply huge load, and carry out testing for several days in tough field environment, field conditions. So the test procedure is quite laborious. You require heavy trucks to carry the equipment. You need to do the excavation to the desired depth, and you need to carry out, several, testing under tough conditions, which is fairly laborious. You require a lot of labor force. You require sophisticated equipment. You require, to transport in the heavy equipment in trucks and so on. Well, from plate load test, you do determine two things. One is the SBC, bearing capacity, maybe ultimate bearing capacity, and other one is settlement. Here you have two equations for finding settlement. Equation for clayey soil, cohesive soil is very simple. SP by SF, settlement in plate by settlement and footing, is equal to BP by BF, width of the plate by width of the footing. You will know the width of the plate. You will have decided what should be the width of the footing. And you'll be knowing from plate load test what is the settlement arrived at under a given plate size. Therefore, SF can be determined. So you can determine the settlement based on these characteristics. So in the same way, you can find out settlement in cohesion less soils also, granular soils also, the equation is slightly more involved. So you use a constant 0.3 when BP and BF are in meters. So this is how the plate load test results are used to determine settlement. Therefore, you have to identify what kind of soil is it. Is it granular or clay soil? And then do your calculation using the appropriate formula. Let us take a few questions here. The plate load test was conducted on clayey strata by using a plate of size 0.3 meter by 0.3 meter. And ultimate load per unit area was found to be 180 kilopascal, 180 kilonewton per meter square. Ultimate bearing capacity of 2-meter wide square footing would be dash. Please note that you are using a plate for the test. Size is 0.3 meter by 0.3 meter. And then the actual footing will be squarish again, 2 meter by 2 meter. From plate load test, it was found that the bearing capacity, ultimate bearing capacity is 180 kilopascal. What is the ultimate bearing capacity for 2 meter by 2 meter footing? I want you to read the problem, read the question carefully. It is mentioned that the type of strata available, the type of ground available is clay soil. If it is clay soil, it has cohesion. Possibly friction angle will be less or even it can be discarded. So, if you take the bearing capacity equation for square footing, we dealt it in the initial days. QF is equal to 1.3 CNC plus gamma D and Q plus 0.4 gamma B and gamma. If the test is conducted on clayey soil, automatically the phi will be 0 and hence n gamma term will go. And whatever is NQ term, okay, it will remain because the test is conducted at the same depth at which the foundation is put. Once n gamma term is gone, whatever is the width of foundation, bearing capacity is not affected. Only for n gamma term, bearing capacity increases with increase in width of the foundation. Therefore, from the question, you should be able to clearly understand that because it is clay soil, phi is 0, therefore, there is no change in the bearing capacity possible, and hence answer is going to be B, that is 180 kilonewton per meter squared or kilopascal. Take this problem. The plate load test was conducted on clayey strata by using a plate of size 0.3 meter by 0.3 meter, and the plate experienced settlement of 2 millimeter. The settlement of 2 meter wide square footing would be how much? First of all, find out the type of soil. It is clay soil. Therefore, you use this equation. If it is granular soil, you have to use a slightly different equation. And then it's mentioned that the plate size is 0.3 meter. The settlement is 2 millimeter. But the footing, actual footing size is 2 meters. Therefore, you find that the settlement is 13.33 millimeters, or SF is equal to 13.33 millimeters. Friends, let us move forward. This is one of the very important tests conducted in the field. Standard penetration test. We sometimes, in short, call it as SPT. SPT stands for standard penetration test. We always say that, this is most abused in the sense that, there are standards are not strictly followed, and every small, practicing consultant, you conduct this test, and there are things which are not taken under control. Therefore, the tests are not fully standardized. Same test on same soil at different places may yield some different results, but still It is one of the most popular tests because it's very convenient. So in standard penetration test, what you do is you try to find out the penetration resistance of ground. If the resistance is more, naturally the soil is said to be stiffer and stronger. If the resistance is less, soil comes under soft soil group. So this test can be conducted either on granular soil or on clay soil. You need a borehole to be made. You insert the probe, which is called, split spoon sampler. Okay, you insert the sampler at the desired location, and then from the top, you hammer the sampler. For that, you use a standard hammer of size 63.5 kgs. Drop it from a height of 750 millimeter. Every time you drop, the sampler will penetrate into the ground. Penetration will be more in softer soil than in stiffer soil. And you try to count the number of blows required. Required for what? So you count, you have the split spoon sampler divided into three parts, each of 15 centimeters or 150 millimeter. Find out how many blows are required for the penetrometer to reach a penetration of 150 mm, then second 150 mm, third 150 mm. That's what you have to count. And then move over to the next depth. So you can take your sampler back, increase the depth of borehole, and then again insert. So this is how the test is conducted continuously till the desired depth is reached. So the test is, clean the borehole approximately about 100 mm in diameter. And then, a thick walled split spoon sampler is driven into the hole using a standard hammer 63.5 kgs, dropped from a height of 750 millimeters. Number of blows required for penetration of sampler into the ground for three lengths each of 150 mm is identified, recorded. Standard penetration number is the number of blows for penetration of 300 mm beyond the seating drive of the first one. So whatever number of blows are required for the next 300 millimeters penetration beyond the seating drive is considered as standard penetration number. If the number is more, it indicates that resistance is more, soil is stiffer. If the number is less, automatically soil is on the softer side. So these are some of the relations for various properties of soil as a function of SPTN value. N is a mere number. So you use N to determine, density of soil. You use N to determine the other characteristics, including allowable bearing pressure of soil. Here is one relationship, given by Teng way back in 1970s or so, and the relationship in the form of an equation like this. So it can be used to determine the allowable bearing pressure. You also can bring out relationship between SPTN value and relative density. So this is what is given by Gibbs and Holtz or Terzaghi and Peck. When SPTN value is very low, you say that the soil is very loose. When SPTN value is more than 50, you say that there is good scope for soil to be stiffer. This graph you find in IS 6403. According to this, SPTN value can be related with phi in granular soils. If let us say SPTN value calculated is 30, then you can show that the angle of internal friction is approximately 36 degrees. If it is 10, standard penetration resistance is 10, then the angle of internal resistance is equal to 30. So this way, there is a correlation between SPTN value and angle of internal friction. You apply two major corrections to SPTN value. One is called correction to for overburden pressure, and the other one is called correction for dilatancy. You also apply correction for energy, but that is not counted in this particular topic. You can always refer to any other standard, method where correction for energy is also given. So now, correction for overburden pressure. Please note that SPT has to be conducted at the ground surface and at different depths below the ground till you reach the bottom where you may put your foundation or whatever it is. Okay. Naturally, soil is one special material which is having a direct relationship with confining pressure. When the soil is at great depth, confining pressure will be high. Automatically, the soil shows more stiffness. On the other hand, identical soil at the surface will show less stiffness. So, you apply the correction for overburden pressure. Correction factor Cn is given by this equation, you will see. Approximately, you can say that sigma is the overburden pressure in kilonewton per meter square. And in case, let us say you consider a soil at a depth of 20 meters or maybe at a depth of 14 meters having density equal to 20 kilonewton per meter cube, then Cn will become equal to 1. So the correction factor for that will be 1. But we find soil either at surface, near the surface, far off from 14 meters, or at much deeper elevations. So you need to apply proper correction. Correction when the confining pressure is less than approximately the actual value or more than the actual value. So you can remember this equation Cn correction for overburden pressure is equal to 350 in the numerator divided by 70 plus sigma in the denominator. All units are in kilonewton per meter squared. So when, let us say, you consider soil at a depth of maybe 5 meters, soil having a density of 20 kilonewton per meter cube, you will notice that the denominator is 170, 100 plus 70, numerator is 350, therefore Cn is greater than 1. So corrected N will always be higher than the actual N measured. On the other hand, when sigma is more, that's when the overburden pressure is more than what you see at 14 meters depth. Okay, so let us say that you are considering a depth of about 30 meters. Then 30 into 26, 600 plus 70, 670 is the denominator, 350 is the numerator. Therefore, the actual N will be lower than the N which is measured. So, depending on the type of the overburden pressure, the correction factor changes. The other test is dilatancy test. Dilatancy test is conducted. I'm sorry, dilatancy correction is applied because SPT test is done by dropping a hammer. That dropping hammer will cause impact, and sometimes this impact may be good enough to cause liquefaction in ground. Usually, light ground having low density is likely to be affected by liquefaction, and hence measured strength will be lower than the actual value. On the other hand, in stiff materials, measured strength can be higher than the actual value. So you need to consider this and hence do apply your correction. So very quickly, we will try to see some of the advantages and disadvantages of SPT, standard penetration test. We like SPT because it is a simple test. It can be conducted by varieties of people. You don't require, serious equipment. You require a hammer. You require it to be dropped from a height. More or less, all other things are not so mandatory. You need a tripod to hold the hammer and so on. The test involves finding n, and this n is a function of many properties of soil. Could be shear strength, could be density, could be allowable bearing pressure, relative density, dynamic soil properties, many, many things. So only one n is sufficient to determine several properties of soil. That's the advantage. Samples collected in split spoon sampler can be used for laboratory testing. You can use the samples to directly do the testing in the laboratory and compare with SPTN value. It's a very quick test. So what you have to do is to have a borehole and hence, conduct the test. It might be just time taken for test, a couple of hours. N can be determined, SPTN value can be determined along the depth in a borehole. So at regular intervals you can determine, therefore you will be in a position to choose the right kind of borehole date. Choose the exact. Uh, yeah. So it can be. You can conduct n. You can find out n at different intervals of time, intervals of distance of maybe 1 meter or so. So you will be in a position to find actual soil properties at every 1 meter depth, or sometimes even zero point 0.5 to 0.75 meter depth. Therefore, you'll be able to identify what is the exact depth at which the foundation can be founded. Some disadvantages. Please note that the test is dynamic because you apply the load dynamically, but you use it for static properties of soil. What guarantee is there that dynamic property and static properties of soil correlate? You don't get continuous results. Usually at 1 meter interval, you get the test results. In very accurate cases, sometimes, especially in places like Japan, 0.75 meter, but it's not continuous recording. Creating borehole is a must. You need to create a borehole. And while driving the hammer, in case a small pebble or so, if it is encountered, automatically the results are boosted up. It appears as if that it's a very stiff soil. Results depend on the experience of the staff members and several other details. So these are some of the main disadvantages of SPT. Well, friends, we'll try to see a few questions. If in saturated fine silty sand, measured value of N is 3, corrected N will it be more or less? So since we say saturated fine silty sand and no mention about the overburden pressure, the kind of correction is whatever I mentioned earlier. So you have, correction for dilatancy, and this is the formula which you have to use. This is the formula which you have to use. Formula. Okay. If the measured value is 3, you see here, you apply here, the actual value will be much, much higher. So put n is equal to 3, and you will notice that, NC will be 9. So the value of corrected n will be more than 3. On the other hand, take this case. You have a stiffer soil, measured n is 33. And what about the actual n? Actual n will be less than the measured n. So the answer should be less than 33. Measured n is actually more than the actual value. Actual value should be 24. You also can think about applying the other correction, overburden pressure. Let us say that you do the test at the surface and n value is 20. What is the corrected n value after overburden correction is applied? Will it be more than 20, less than 20, or equal to 20? Naturally, the correction factor Cn is equal to 350 divided by 70 plus sigma. Sigma is 0 in this case, therefore it is 5. So corrected value will be 5 times the actual value of n. Therefore, it is much, much more than 20. Answer is A. On the other hand, if a SPT is measured at a depth of 50 meters, the measured value is 20. Then the actual overburden pressure after applying the correction will show that the SPT n value, corrected n value, will be less than that. So the answer should be B. Why? You know, Z is equal to 50-meter depth, and then you will be applying the density of the soil. Therefore, Cn, which is 350 divided by 70 plus sigma, the value of Cn will be much less than 1, and hence the corrected n is lower than the actual n. In this case, it is found to be 6 point something. You round it off to the lower number, little more on the conservative side. Therefore, corrected n is 6. Corrected n is 6, much less than 20. Therefore, the right answer here is B. The other important test is CPT, cone penetration test. It's also called Dutch cone penetration test. It's quite popular in Europe. IS code for this is 4968 part 3. It gives continuous record of the penetration resistance. Main body consists of the cone of size 35.7 millimeter in diameter and 60-degree vertex angle. Cone is carried at lower end and of a steel rod that passes through a steel tube of 36 millimeter diameter. Either the cone or the tube or both of them can be forced into the soil using jacks. So this is how the test equipment would be, and the CPT is conducted at this depth. And you will be in a position to determine the resistance for the penetration of the static cone. So, as I said, it consists of number one, a cone, a rod with a cone, which can be pushed separately, a sleeve or steel tube, which can also be pushed separately, or both of them can be pushed together. So, cone penetration test, either the steel tube or cone or both can be forced into the ground at a very slow rate. The rate at which it is penetrated into the ground should not be more, approximately 20 millimeter per second. Why should it not be more? If it is more, automatically there will be some disturbance due to high speed with which it is penetrated, and hence you may not get the actual results. Cone penetration resistance is sum of the resistance for pushing cone by 8 centimeters, and then pushing the steel tube also by 8 centimeters, and then finally pushing cone and the tube simultaneously for the next 20 centimeters. So it is expressed as in kilonewton per meter squared, as QC is equal to QC1 plus QC2 plus QC3. So this is how cone penetration test is planned, and these are some of the typical results from cone penetration test. So advantages, it's a static test, unlike SPT. So test is conducted simultaneously, continuously by pushing the cone penetrometer. Continuous recording of the resistance is possible, unlike in case of SPT. It correlates with SPT very well. Therefore, all properties of soil can be determined. This test can separate skin friction from tip resistance. Please note, this is one of the biggest advantages of CPT, because when you do when you think of providing pile foundation, You need to know how much is the capacity under skin friction, how much is the capacity under tip resistance. Based on that, you can plan your piles. Therefore, this test can separate out skin friction from tip resistance, and it is particularly preferred in soft clay. Disadvantages, it is more tedious to do this test than SPT. Results can be affected by the speed of penetration. Test requires, costly equipment and more skilled labor. So, one more question. Group 1 enlists in situ field tests carried out on soil. Group 2 provides list of parameters for subsoil strength characterization. Match these two. You know, in group 1, PQRS, you have pressure meter, SCPTs, SPT, and then vane shear test. In group 2, you have Menard's modulus, number of blows, skin resistance, and undrained cohesion. So naturally, pressure meter test Menard's modulus. SCPT, it is the skin resistance. SPT is number of blows, and vane shear test is undrained cohesion. Therefore, answer is A. P1, Q3, R2, S4. Okay, friends, let us move forward to learn about stress distribution in soil. All of you know that there are two types of stresses possible. One is geostatic stress, that is, stress at any level in the ground because of the overburden on top of it. So, the deeper you go, the geostatic stress keeps increasing. The other one is stress due to some new structure which is built. So, we need to consider these two to find the total stress acting. So, to determine stress distribution due to new structure which is put, you do it separately, which you call as determination of stress distribution of soil. To that, you can add geostatic stress and hence find out the total stress. To find the stress distribution in soil, you have a big challenge because several properties are governing the stress distribution. So there are different methods by which you can formulate, you can determine. We'll quickly see them. As I said, geostatic stress is the stress due to the overburden. If I take a soil at this depth, at a depth equal to Z, it is subjected to the vertical stress equal to Z into gamma density. And when Z increases, the pressure also increases. At Z is equal to 0, pressure will be close to 0. This is what is geostatic stress. Then you have stress due to external load, as I have shown here. Any load you put on soil, it's going to cause extra stress. And that's what we need to determine. And it could be a aeroplane which will, which will do the landing, at which time, heavy dynamic force acts on the ground, or it could be a truck, it could be some penetration of a rod, or it could be any building. So all of them cause external load, and all of them cause stresses on ground at different depths. You have different, researchers who have worked on it using the principles of theory of elasticity. Bosnick made bulk of the work, and he made the work. Arrived at the formulas, for different types of loading. So I wish you remember this equation. Okay, I wish you by heart this equation. If you have a point load is only theoretical of magnitude P, then the stress at any level is equal to sigma z, or delta sigma z equal to q by z squared into this formulation, where z is the depth under consideration and r is the radial distance. So I want, friends, you people to somehow remember this equation. You may not remember the other equations, but this will be quite handy for you. So q by z squared into 3 by pi, 3 by 2 pi to 1 over 1 plus r by z whole squared to the power 5 by 2. Bosnick also gave equations for other types of loading, but Bosnick's equation, particularly for point load, some of the assumptions made are that soil is linear, elastic, homogeneous, isotropic, continuous, and semi-infinite. Most of the times we resort to this assumption. Medium, that is soil medium, obeys Hooke's law, so stress is proportional to strain. Self weight is ignored. You only consider the additional weight due to the structure. You assume that soil is not stressed before. This is the assumption with which you work. And you also assume that there will be no change in the volume of the soil because of the load. Top surface is assumed to be level, assumed to be horizontal, and then it is assumed to contain no shear stress. So according to Bosnick's theory for point load, you have bulbs like this which you call as pressure bulb. Each of this bulb represents the contour of some equal stress property. You go for bigger diameter, automatically the pressure decreases. The deeper and deeper you go, the pressure decreases. Radially you go further and further, the pressure decreases. So if you try to plot the stress, vertical stress in soil, just below the load it will be maximum. You go away radially, it keeps reducing. In the same way, you think of going in a vertical direction. The deeper you go, the pressure is going to reduce. But then you have a interesting point that the pressure is going to be maximum at a depth, something like this, where beta is given by 39.15 degrees. This is the equation for circular load which is in the form of a circle, uniformly distributed load. And I'm not going to explain this. This is the equation for line load. So you see this load, it extends, perpendicular to the board, perpendicular to the sheet here, for a sufficient distance. And the equation is given by this. Then you have a strip load to be considered. And then you have rectangular load to be considered. Therefore, in all these cases, you find out the stress due to the external load. So if I assume that the load is P or Q, then you have pressure bulbs like this drawn. The first bulb, shows this is the contour of equal stress. So it shows maximum stress. You go deeper and deeper, the stress is going to reduce. Then you should have a good idea about contact pressure. Contact pressure is the pressure in soil at the point of contact with the footing. Please note that this contact pressure in soil depends or is a function of how flexible the footing is. It's a function of type of the soil. It's a function of the depth of embedment. So if you consider a flexible footing, I'm sorry, this is rigid footing. Okay. So please treat this as rigid footing. A flexible footing. Then whether it is cohesive soil or cohesionless soil, the distribution is uniform. Only thing is, because the footing is flexible, it will experience more settlement at one place and less settlement at the other places. In clay soil, it will experience more settlement at the center. On the other hand, in sandy soil, it is just a reverse. In case of rigid footing, you will see that the footing is so rigid, therefore there is no deformation of it. However, the stress distributions are different. In clay soils, The stresses at the edge are more. On the other hand, in granular soil, stresses are more at the center because of the confinement. This is how the effect of rigidity of the footing, effect of soil type are considered for contact pressure. Also, depth of embedment will influence. The deeper you go, the change in the value. For example, in granular soil, pressure at the edge is zero and it is maximum at the center. So that pressure, it will not be zero here, and it will not be too high also at the center. It may be moderate value. So that kind of property change is possible because of the depth of embedment. So contact pressure is dependent on the rigidity of the footing, type of the soil, and depth of overburden. Some problems. Contact pressure and settlement distribution for a footing are shown here. The figure corresponds to, you can see here, the contact pressure is zero here, maximum at the center. Therefore, it corresponds to granular soil, and the footing, since the pressure is not uniform, the footing is rigid. So, rigid footing on granular soil, therefore, answer is A. A load of 500 kilonewtons is acting on the ground surface. Based on Bouchnik's theory, ratio of vertical stress at depths of 2 and 4 meters right below the load given by, you know, right below the load R is 0. Therefore, this entire bracketed term will be equal to 1 and equal to 3 by 2 pi. So, this is a constant. So, at depth Z equal to 2 meters, the intensity will be Q by 4. On the other hand, at depth Z is equal to 4 meters, intensity will be Q by 16. Therefore, vertical stress at 2 meter to vertical stress at 4 meter will be ratio equal to 4, and hence answer is D. Likewise, you consider a situation. I read the question paper. Question: a vertical stress at point P1 due to point load Q on the ground surface, as shown in the figure, is sigma here. According to Bouchnik's theory, the vertical stress at P2 here, which is at a distance equal to R by 2 radially and Z by 2 vertically. So R by 2 and Z by 2, this ratio is going to be the same. Therefore, no change, and hence entire bracketed term is going to be constant. So in the first case, it is Q by Z squared. In the second case at P2, it is Q by Z by 2 whole square. So variation is 4 times sigma. Therefore, answer is D. So friends, you may have, situations like this where you need to find the stress in soil because of the new structure which is built. Add it to the geostatic stress and hence find out at different depths what is the stress level the soil is subjected to. If it is more than the strength, you have to be concerned. Otherwise, you can be safe. Let's quickly go over to the next topic, stability of slopes. That is a big challenge. You must have, heard in the news every time in North India, especially in Uttarakhand, where people go for pilgrimage to Badrinath, Kedarnath. You will see one landslide or the other, hampering the, daily routine life. So, slopes are grounds which are inclined and they are quite vulnerable and they are likely to experience slide. And we should be able to identify whether a given slope is stable or not. And many reasons are there to cause the slope to become unstable. Slope is an exposed ground surface that stands at an angle which is different from that of horizontal. Which is inclined at some angle to horizontal. Slope can be natural or man-made. Unfortunately, there have been many instances of slope failure in the past, in the present, killing not just hundreds, thousands, tens of thousands of people, continuously. There are many causes for the failure of slopes. It could be the gravitational force, it could be heavy rains, it could be, groundwater table suddenly experiencing rapid drawdown, seepage water, volcanic eruption, earthquake, human activity, erosion due to wind and water, external load. But the major culprits, I tell you, friends, is one is rainfall, other possibly is earthquake, third one is human activity, which you have to consider. If you can control these, possibly many of the slopes can be controlled. So here is one landslide which happened in 2014 in Maharashtra, killing about 160 people and probably wiping off entire village. More than 45 houses were buried. This is how the place looked like. And after the landslide, it looked like this. It was all because of heavy rains. So people tried to determine, or people tried to explain what were the reasons for the failure like this. So slope can fail because of the slide that can happen. And the slide can be in the curved form, rotational slide, or it can be translational. It can be, in the planar form. So it all depends upon the kind of soil that exists in the slope. Okay, it can be either rotational in the form of a circle, or curved shape, or translational. Slope stability analysis basically includes determining the potential failure surface, the place in the failure surface, whether it is a translational, like in the form of a plane, or it is in the form of a curve. So you have to identify the potential failure surface, which is a challenge, and then the forces which cause the slip. You also will have to identify the forces which resist it, which stabilize. So that's the strength. And you have to guess, you have to decide on what should be the margin of safety, factor of safety. So these are the four basic things which are determined in slope stability analysis. But because the soil is heterogeneous, the slopes not being of uniform type, okay, it's challenging to determine the desired margin of safety. In general, factor of safety is the ratio of strength at the numerator and the stresses caused in the denominator, or restoring force in the numerator, disturbing force in the denominator. So, whenever the strength of the ground is high, automatically the factor of safety will be good. Whenever the stresses are high, stresses can be high because of the human intervention, stresses can be high because of heavy rains, stresses can be high due to earthquake, due to volcanic eruption, automatically factor of safety is going to reduce. You have to check whether the factor of safety is much higher than 1. Therefore, possibility of slope failure is less. Broadly, you can divide the slopes into infinite slope and finite slope. As the name itself indicates, infinite slope is one which extends to great length, both at the top as well as at bottom. So these are the slopes that have dimensions that extend over great distances, and the soil mass is inclined to horizontal like this. So here, if you consider, first thing you have to consider is the plane at which the slide can happen. It may be at some thickness, some depth below the ground surface. You take a small wedge of soil, okay, having a weight W, find out the shear stress which causes the slide, find out the resistance, and resistance to shear stress will give the factor of safety. That's what you need to do. So you find out the factor of safety, which is equal to resistance or restraining force to the sliding force. And factor of safety is equal to tan phi by tan beta, where phi is the angle of internal friction, that's the strength, beta is the slope angle. So in a homogeneous soil where you don't consider the effect of groundwater table, factor of safety is equal to tan phi by tan beta. So when the soil has good strength, such a way that phi is greater than by beta, factor of safety will always be higher than 1. So possibility of slope failure is minimized. The maximum inclination of infinite slope in a cohesionless soil for stability is equal to angle of internal friction of soil. The limiting angle of inclination for the stability of infinite slope, you know, in cohesionless soil is as shown here. So whenever the phi of soil is more than the slope angle, you can take it for granted that the slope is stable. Whenever phi is less than the slope angle, it is going to be unstable slope. So Moore Coulomb criteria gives you the factor of safety equal to 1. So a slope which is at this in this line is just on the verge of failure, it is having a factor of safety equal to 1. You can also consider the effect of seepage. As I said, one of the major culprits for the slope failure is the rainwater. Because of the presence of rainwater, the soil will become weak, soil will lose its strength. In addition, water seeps through the slope and goes to the lower side. And whenever water seeps like this, it erodes the surface, causing the slope failure. You can very easily show that whenever you consider the seepage effect, factor of safety, we already found in the previous slide that factor of safety is equal to tan phi by tan beta. In this case, factor of safety is equal to tan phi dash you use to show that it is the effective stress which you consider, effective friction angle which you consider, okay, and multiplied by gamma dash by gamma sat. Gamma dash is the submerged density, gamma sat is the saturated density. So you use gamma sat to find the total stress. Naturally, you need to consider the effect of water. On the other hand, for finding the strength, it is only the strength of the soil which you have to consider, not this water. Therefore, you need to consider gamma sub. So, friends, I want you to remember this equation. Factor of safety is equal to gamma dash by gamma sat into tan phi dash by tan beta. So, you can solve a number of problems were asked in the previous question papers. I read down the first problem. A long slope is formed in a soil. Whenever I say long slope, it is infinite slope with shear strength parameter c equal to 0 phi, c prime equal to 0, phi prime equal to 34 degrees. So it is a cohesionless soil. Effective strength in terms of friction angle is 34 degrees. A firm stratum lies below the slope, and it is assumed that the water table may occasionally rise to the surface. So sometimes, water table can even rise to the surface. So you need to consider the worst situation. Okay. With the seepage taking place parallel to the slope, use gamma sat equal to 18 kilonewton per meter cube, gamma w equal to 10 kilonewton per meter cube. The maximum slope angle to ensure a factor of safety of 1.5. Assuming potential failure surface to be parallel to the surface slope would be dash. So you know that factor of safety is given by gamma dash by gamma sat into tan phi dash by tan beta. Phi dash is 34. Beta is what you need to find out. Gamma dash is the submerged density, that is gamma sat minus gamma w. In this case, gamma sat is 18, gamma w is 10. Therefore, gamma dash is 8, gamma sat is 18, phi dash is 34. only unknown beta is determined, which is equal to 11.3 degrees. Very similar question. An infinite sand slope shown in the figure is on the verge of sliding failure. Therefore, factor of safety is 1. Groundwater table coincides with the ground surface. Okay, so groundwater table also is somewhere here. Unit weight of water is so much. Saturated unit weight is so much. So unit weight is 9.81 kilonewton per meter cube. Saturated unit weight is 21 kilonewton per meter cube. The value of effective angle of internal friction in degrees up to 2 decimal places in the sand is given by same equation. Gamma dash is equal to 21 minus 9.81 equal to 11.19. Gamma sat is directly 21. Phi dash is uh, given here. Yeah. And then, beta. So you take factor of safety is equal to 1 and everything is given. Therefore, beta here will be equal to 20 degrees. Okay. Likewise, you have the other problem also very similar to that. You know the friction angle, you know the density, you can find out. And with this I close my lecture, because I thought I would spend a little time on Coulomb's theory of earth pressure. And it's basically the theoretical explanation with lot of assumptions to be considered. And hence, you have the wedge which is to be considered. And finally, you need to determine the forces acting on the sliding wedge. W is the weight, and then R is the resistance, soil reaction, and then you have the active earth thrust, PA. So PA is determined using most of the times, graphical method. So there are certain advantages and limitations of Coulomb's theory over Rankine's theory, but the most of the problems can be solved using Rankine's theory. Friends, with this I close my lecture, mentioning to you that there are lots of areas in which you can get a gate type of questions. You can refer to them. And I conclude mentioning that whatever I have dealt with is very important considering the history of gate examination. So I did cover bearing capacity and shallow foundations, deep foundation, soil stabilization, retaining walls, stability analysis of slopes, stress distribution. I just wish all of you good luck. And we had a wonderful gate training program. We have the last session, due now. Thank you very much.
Thank you very much, sir. I'm pretty sure that all our GATE aspirants would be very beneficial from this session. Thank you once again. So all of you will have 15 minutes of break and will join back again at 3:45 p.m. for the second session on air pollution, shared by two of our professors from Department of Civil Engineering, Professor Sharmila A. and Professor Shilpa B.S. So see you all at 3:45 p.m. Thank you.